Let's begin our topic on chemical kinetics. The term kinetic energy means energy of motion. When we think of that word kinetic, we're thinking how fast reactants are turning into products. It's usually measured in something called molarity per seconds. How quickly something is disappearing is the rate at which reactions are measured. When a reaction is said to be spontaneous, it doesn't necessarily tell us how quickly the reaction is occurring. Our car, for instance, made of steel, will rust. It is a spontaneous reaction. That particular reaction could take many, many years to actually see a product occur. Some reactions occur within split fractions of a second. We have radioactive decay, for example, of large elements past uranium on the periodic table that are so unstable, their process of decay occurs in thousandths of a second. That's a very quick reaction. So that term spontaneous doesn't give us an indication of how long, just the fact that it is occurring. The term kinetics, then, the topic of our chapter, is referring to how quickly a reaction occurs. And what are those things that we could do to control the speed? If we want a reaction to go faster, what might be some ways to manipulate the equation to increase its speed? Or if we're trying to control a reaction, what could we do to slow it down? So the topic of kinetics, how fast a reaction is occurring. In our notepad then, we have a chapter 14 on chemical kinetics, and between the PowerPoint slides and the notepad, we'll be filling those in together. It says we study kinetics by studying reaction rates. How quickly a reaction is occurring, the study of kinetics. Spontaneous reactions. The word spontaneous means that the reactions are happening, but not any indication of how fast those reactions are occurring. Another topic in our chapter, how do the reactants actually turn into products? The step-by-step reaction mechanism will be discussed as well. Knowing the speed of a reaction gives us great insight into a reaction mechanism. And again, more on that, but most reactions occur in a multi-step process. Knowing how quickly a reaction occurs or how slowly a reaction occurs allows us to propose these pathways called reaction mechanisms. There are many things we can do to manipulate the effect of reaction rates. What are some things we could do to speed up or slow down? Well, one of the factors that says the physical states of reactants. The physical states of reactants determines, are they solids, are they liquids, are they gases? What are those physical states? We know that more readily that molecules can collide with one another, the more rapidly they react. They physically have to come into contact with each other to cause reactants to turn to product. So I can see gases and liquids. Those are solutions that are easily mixed. Gases with complete freedom to move around, they're going to collide more often, and therefore reactions will occur faster. Solids, of course, are limited to the surface area for their reactions. Crushed powders actually have a faster reaction rate than larger tablets. So again, crushing or liquefying or creating a gas will increase the rate of a reaction. If we think about the collision theory, and just that simply stated says, in order for a reaction to occur, molecules have got to collide with one another. That's how bonds are broken and new bonds are formed. We can affect the reaction rate by manipulating the concentration of our reactants. If I put more in, I'm more likely to have a collision. So if the concentration increases, more solute is provided. We have a frequency at which reactant molecules collide increases, and that would thus lead to a faster rate. The more stuff, the more likely they are to collide. A third way to manipulate a reaction rate is to control the temperature. Most often when we increase temperature, The reaction rate increases as well, simply because those molecules possess more kinetic energy. More kinetic energy means they're moving faster, and more collisions will occur with that higher energy. And on the flip side of that, it's why we refrigerate foods. If I place them into a cold environment, the reaction rates slow down, the process of spoiling is inhibited. The fourth thing we can do to affect the reaction rate is the presence of a catalyst. Catalysts are not heat, but they're actually ingredients that we add to actually alter the pathway of a reaction mechanism to speed up a reaction. If we think about an energy profile, and I'll just draw a typical exothermic reaction, we start with reactants, and over time, we go to products. And just think of this really as, let's just call this energy, kinetic energy, versus time. If the reactants start at a certain energy, they must climb a certain barrier known as activation energy. How much energy do we have to input to cause the reaction to occur? And that term is called activation energy. If there's a large barrier, not many molecules make it over that hill, and we have a slow reaction rate. If we have a smaller energy barrier, a lower activation energy, more molecules meet the requirement, and we have a faster reaction rate. A catalyst works by lowering the amount of activation energy. It actually provides an alternate pathway for the reactants to find the products. If we have a smaller activation energy in the presence of a catalyst, we will increase the rate of our reaction. So the four factors that affect reaction rate, the physical states of reactants. Are they solids? Are they liquids? Are they gases? We know the more energy they have, such as gas molecules, the more likely they are to collide. Number 2, the concentration of reactants. As concentration increases, we're more likely to have collisions, and therefore rates will increase. We can increase temperature, causing more energy in those molecules to collide more frequently. Or the fourth one, we could add a catalyst to speed things up. A catalyst is a chemical that we add. It is not a reactant, not a product. It's just there to change the pathway, to change the mechanism in which the path occurs. Lowering the activation energy increases reaction rate. If we measure the reaction rate as the change in concentration of reactants or products per unit time, we understand that as reactants get consumed, products are formed. The amount of reactants goes down, the amount of products actually increases as time is going by. So if we think about a hypothetical reaction where we have just reactant A turning into product B, A is disappearing as B is appearing. Reactants are used, products are made. If I think about how to express that rate, rate is equal to the change, and that's the delta sign, the change in the disappearance of reactant A over a set time interval, delta T is change in time, which would be equal to the rate of appearance of the concentration of B over the change in time. Reactants get used, that's the negative sign. The concentration of reactant decreases per unit time interval as the amount of product, B, is being formed. That's the positive sign. So as reactants get used at the same rate, products are formed. If I think about the concentration of B at time 2 versus the concentration of B at time 1, that's what the change is representing. So rate really is an expression of the change in concentration per unit time. And I'm going to put brackets to show concentration most often is measured in molarity units. The change in concentration per unit time. And that's the delta T part. So suppose instead of generic letters A going to B, we look at a familiar equation where nitrogen combines with hydrogen to form a molecule called ammonia. And we see a 1:3:2 stoichiometric ratio. We would notice, and just kind of thinking about this in terms of an XY axis, let's suppose, let me get my camera shifted a little. Let's suppose on an XY axis, we think about what's happening. We have a certain amount of the reactants, hydrogen and nitrogen. Time is going by and the concentration of hydrogen goes down. Reactants are consumed. Nitrogen also goes down. And notice what I'm trying to draw is that the rate at which hydrogen disappears is 3 times that of the rate at which nitrogen disappears. And at time 0, we wouldn't have any product, but eventually product would form, and it would be right between the nitrogen and hydrogen. So the concentration of hydrogen going down at 3 times the rate of the concentration of nitrogen, and twice that for the production of ammonia. Just a visual of what's happening in terms of kinetics. The reaction progresses and the concentration of hydrogen goes down. Reactants get used. As the reaction progresses, the concentration of nitrogen goes down 1/3 as fast. Want over given ratio, 1/3. All as the reaction progresses, the ammonia molecules goes up, and it's going to lie right between the two with its coefficient of 2. 2 moles worth of ammonia are formed. And I've shown that by drawing those 3 lines onto a set of axes. Reactants get used as products get made. If we want to calculate rates, we have many different ways to do that. The 2 that are provided in our text are known as average rates. And average rates are taken over long intervals of time. For example, if I have an initial concentration of 1 molar and it dropped to 0.9 molar in a course of 10 seconds, this is a reactant decreasing in concentration, we would solve that by noting the change in concentration of our reactant over the change in time. It's an average rate. The second way we could calculate a rate is known as an instantaneous rate. I didn't spell it right. Instantaneous rate. There's not enough N's. An instantaneous rate. That's determined by finding the slope of a line tangent at the curve at any given point, because the rate isn't changing over time, it's happening at an instant. It's known as a derivative to the calculus buffs out there. Let me represent these in terms of a graph. An average slope method says, thinking about as time going by, we're measuring the concentration of a reactant. We'll call it reactant A. As time goes by, we notice that reactants get used, so their concentration decreases. If I take an average slope method, I find a time interval. When I think about how much the concentration changes per unit time, I'm finding an average rate. It's the rate of a reaction. I'll write that RxN, the rate of a reaction over a particular time interval. That example might show the change in concentration would be initial of 1 molar, final of 0.9 molar, and I'll reverse that to show I know that reactants get used, so it will come out negative, over a course of 10 seconds. how much the concentration changed by a certain time frame, an average slope method. A second way to calculate that, and let me represent that on a graph, is called an instantaneous slope. Let's consider the same set of XY axes, concentration versus time, and we'll just call it reactant A. I'd like to know how fast the reaction is occurring at an instant in time. Not over an interval of 10 seconds, but right here at this time. How fast is it occurring? We do that by taking the tangent to that curve at that particular instant in time. So the rate of a reaction at a certain time is called an instantaneous slope method. An average slope, we need two time intervals. How much the concentration occurs over a time interval. An instantaneous slope, how fast is that reaction going right now? And that's considered to be an instantaneous slope by finding the tangent. Stoichiometry and reaction rates. In general, if we look at an equation with generic letters, where the little letters are representing the coefficients and the capital letters are representing the reactants going to products, we have reactant A with its coefficient of A reacting with B to form C and D. How would we represent the rate of that equation? Well, this rate is given by, again, negative, because we are looking at reactants disappearing, the fraction of the coefficient, 1 set over A, representing the coefficient of reactant A, times the concentration of A over the change in time. That is set equal to negative 1 over B times the concentration, the change in concentration of reactant B over the change in time. Reactants disappear, so we place a negative sign. Products up here, they'll have a positive value. The change in concentration of C over the change in time, and 1 over little d representing the coefficient over the change in concentration over the change in time. So stoichiometry ends up to say we're looking at the ratio at which reactants disappear compared to products as they appear. Let's take a look at a real example. We'll take a look at the example we've used many different ways, making ammonia. Let's express the rate in terms of stoichiometry for 1 mole of nitrogen consuming 3 moles of hydrogen to form 2 moles of ammonia. This is called the rate expression. I'm going to write that down because we have a lot of language to learn. The rate expression. We must not confuse that with the rate law of a next lesson. The rate expression uses stoichiometry. The rate of this reaction in the production of ammonia would be represented by negative 1 over 1 times the change in concentration of nitrogen over the change in time. And yes, you're correct, it's not necessary to show 1 over 1, but it's nice to see that if the coefficient of nitrogen is 1, this is how it would be included. Set equal to negative 1/3 the change in concentration of hydrogen over the change in time, set equal to positive 1/2 the change in concentration of ammonia over the change in time. Hydrogen disappears at 1/3 the rate of nitrogen. Ammonia appears 1/2 the rate of nitrogen. The rate expression uses stoichiometry, remembering to place under a fraction the coefficient in front of reactants and products. If we look at a you try it example, it produces a decomposition from ozone forming molecular oxygen. How is the rate at which ozone disappears related to the rate at which oxygen appears in the following reaction. The rate at which ozone disappears, and there's the negative sign to remind us that it's disappearing, would be negative 1/2 the change in concentration of ozone over a change in time, set equal to 1/3 the rate at which oxygen, molecular O2, forms over a change in time. So with stoichiometry, a rate expression, that ozone disappears with a fraction of 1/2 set equal to oxygen, molecular oxygen, appearing with its fraction of 1/3. We might even be asked to number crunch. If the rate at which oxygen appears is 6.0 times 10 to the negative 5th molarity per second, notice this is a rate, molarity per second unit. If oxygen is appearing at 6.0 times 10 to the negative 5th molarity per second at a particular instant in time, what rate is ozone disappearing at the same time? Well, here's what we know. Negative 1/2 is equal to the concentration of ozone changed over change in time, set equal to 1/3 the rate of appearance of oxygen. That rate of appearance is given to us as 6.0 times 10 to the negative 5th molarity per seconds. That's the unit for rate. We're being asked to solve for this part of our equation. How quickly does the ozone disappear if we have the rate at which oxygen appears? And now it's just algebra. We want to get this by itself. The change in concentration of ozone over the change in time is our target variable. Why don't we start by multiplying both sides by 2 to cancel the fraction of 1/2? We could see now that the change in concentration of ozone over the change in time is equal to 1/3 times 2. I think I'll simplify that by just showing this 2/3 of 6.0 times 10 to the negative 5th molarity per seconds. I certainly can just hit that all out on my calculator. We'll get the same answer. So please grab your calculator and hit with me. I'll hit by hitting 2 divided by 3, 2/3 of 6 times 10 to the negative 5th units, and I find 4 times 10 to the negative 5th. So this side of our fraction is 4 times 10 to the negative 5th, and the unit there is representing a rate. At what rate is ozone disappearing? And rates are given units of molarity per second. Oxygen is appearing at 6 times 10 to the negative 5th molarity per second units. The ozone is disappearing with the rate of 4 times 10 to the negative 5th. Let's try one more practice with average rates, the rate expression that uses stoichiometry. It says the decomposition of dinitrogen pentoxide produces nitrogen dioxide and oxygen gas. Let me reread that, see if we have our skeleton correct. The decomposition of dinitrogen pentoxide produces nitrogen dioxide and oxygen gas. We have our skeleton. Let's work to balance the equation. Well, I could start here by doubling the n's, but then I still end up with an odd number of O's. So I think, let's try this. I'm going to double this, get 4 n's, and see if this even number of O's can work over here. We have 10 O's on the left, 8, 9, 10 on the right. So a 2, 4, 1 balanced our equation. If the rate of decomposition of the reactant at a particular instant in a reaction vessel is 4.2 times 10 to the negative 7th molar per second, what is the rate of appearance of our two products? Well, let's get our stoichiometry set. Negative 1/2 times the change in concentration of our reactant over time is equal to, and let's just target that first product, it would be 1/4 times the change in concentration of NO2 over the change in time. They're letting us know that the reactant rate is decomposing with a rate of 4.2 times 10 to the negative 7th molar per second. Let's pull out this expression, the change in concentration of NO2 over the change in time. If we'd like this side by itself, we'll need to multiply both sides by 4. And friends, disregard the negative sign. It's there by convention to let you know reactants are disappearing. We will never, ever, ever have a negative rate. It'd be like driving backwards down the highway going negative 55 miles per hour. It makes no sense. Rates are always positive. So what we'll end up hitting is 4/2, 4 times 1/2, times the rate that was given of 4.2 e negative 7. And I find 8.4 times 10 to the negative 7th molarity per second. That was our first product. We were actually asked to solve for both products. Well, that same ratio, and again, I'm putting negative to remind us that it's disappearing, but rates are always positive. The rate at which our reactant is disappearing, 4.2 times 10 to the negative 7th molarity per second, is equal to, and notice the coefficient here is a 1. So it's equal directly to the change in concentration of the oxygen over the change in time. And that's what we were asked to solve for. So this one is as easy as hitting 1/2 the original rate. So 4.2 e negative 7 cut in half gives us a value of 2.1 times 10 to the negative 7th molarity per second as the change in concentration of oxygen over the change in time. And that represents the rate at which oxygen is being made. Reactants are consumed. That negative sign is there by convention. It is not showing that we have a negative rate.